We are diving immediately into the paper. NVIDIA Nemotron 3, Efficient and Open Intelligence.
Right, and this is a big one. It's all about how NVIDIA is aggressively tackling the efficiency frontier. They've introduced the Nemotron 3 family, that's Nano, Super, and Ultra.
And the immediate takeaway seems to be this powerful balance. You're getting state-of-the-art agentic and reasoning capabilities, but it's all built on a pretty radical new hybrid architecture.
Exactly. That architecture is really the centerpiece. It's a novel hybrid mixture-of-experts, MoE, that combines Mamba with the traditional transformer.
And that combination is transformative for speed.
Absolutely. The Nemotron 3 Nano, which is the smallest version, shows this off perfectly. It gets, up to 3.3 times higher throughput compared to similar models.
And crucially, it does that without sacrificing accuracy.
Not one bit. And beyond just speed, they're aiming for scale. These models support an ultra-long context length of up to 1 million tokens.
Which is just essential for any serious agentic work.
And the bigger models, Super and Ultra, use some really cutting-edge training ideas. Things like LatentMoE, which boosts quality without more inference compute. And they're trained using the NVFP4 number format for just insane throughput.
And I think for the whole community, the commitment to openness here is huge. NVIDIA is promising to release the model weights, the training software, the recipes, and the data set over 10 trillion tokens of it.
It's a full package.
Okay, let's unpack that core architecture first, because that hybrid Mamba-Transformer choice feels like the real strategic foundation here.
It is. The mission statement for Nemotron 3 wasn't just, let's be more accurate. It was to push the accuracy to inference throughput frontier.
Specifically for these complex multi-agent environments where you might have tons of simultaneous calls.
Or just really long outputs. Traditionally, we interleave MoE layers with self-attention layers. Self-attention is the powerhouse, we all know that, but it has this unavoidable cost.
It gets more and more expensive as the output grows.
Exactly. So the big innovation here is swapping out most of those expensive self-attention layers for Mamba 2 layers. If you look at the diagram for Nemotron Nano 3, it's pretty much all MoE and Mamba 2, with just a few self-attention layers sprinkled in.
So break it down for us. Why is Mamba 2 the cost saver here, especially in a long generation scenario?
It all boils down to the key value cache, the KV cache. With self-attention, when you generate a new token, the model has to attend over a cache that grows linearly with the sequence length.
Right, so if you're generating a 16,000 token output, that memory requirement and the compute just balloon.
It becomes a massive bottleneck. Mamba 2, on the other hand, relies on a structured state space model. And what that means is that it only needs to store a constant state during generation.
So the resource footprint for Mamba 2 just stays fixed no matter how long the output gets. That's the dream for anyone trying to manage VRAM and latency in production.
Precisely. That fixed computational budget is the key. And when they ran benchmarks on common reasoning workloads, like, say, an 8K input sequence that generates a 16K output, the efficiency difference was just stark.
We mentioned that 3.3 times jump. Can you give us that specific comparison again?
Yeah, the Nemotron 3 Nano 30B model achieved 3.3x higher throughput compared to a pure transformer MoE of a similar size, something like Quinn 330B. For anyone running large-scale agentic apps, that is a game changer for your operational costs.
But wait, if Mamba is so much more efficient with its fixed memory cost, why keep any attention layers at all? Why not just go pure Mamba MoE? What's the trade-off?
Yeah, that's the excellent engineering decision they made. Attention is still king for high-fidelity, all-to-all information routing. Mamba is fantastic for sequence modeling, but for those key moments where the model needs to synthesize information across the entire prompt.
Like at the beginning of a complex reasoning chain.
Exactly. You still need that global connectivity that self-attention provides best, so it's an engineered synthesis.
Okay, so MoE for sparse parameter scaling, Mamba 2 for the efficient sequence modeling, and then you just slot in attention where that global information routing is absolutely mandatory.
That's the summary. They're leveraging the strengths of each part to optimize for deployment while minimizing any accuracy drop-off.
And that optimization theme continues right into our next section. After optimizing the core architecture with Mamba, the next logical step is optimizing the parameters themselves. And that brings us to LatentMoE.
Which is a feature for the larger Super and Ultra models, and it is absolutely a hardware-aware design. The paper explains that MoE bottlenecks are different depending on whether you're optimizing for latency or throughput.
Right. If I want low latency, a quick response, my model is memory bandwidth bound. I'm just waiting to load those expert weights.
Correct. But if you're focused on high throughput, maximizing tokens per second, the bottleneck shifts. It becomes all-to-all communication volume, which is the data being shuffled between chips.
Okay, so how does LatentMoE solve this? It sounds a bit like a free lunch.
It's not quite a free lunch, but it's a brilliant dimensional shrinkage trick. The core idea is that tokens are first projected from the model's hidden dimension, let's call it dollars, into a much smaller, latent dimension, $1.
And all the expensive expert routing and computation then happen in that compact space.
Yes. That reduction in size, from dollars to dollars, immediately cuts down the amount of data that needs to be moved around, typically by about 4 times. But here's the crucial move. They immediately reinvest that saved capacity.
So they take the computational budget they saved by shrinking the dimension, and they use it to scale up the number of experts and the number of active experts.
Exactly. They keep the active computational budget, the total number of parameters processed, the same. But by increasing the total number of experts, you get more diversity. And by increasing the number of active experts, you get more nonlinearity.
So you're processing the same number of active parameters, but those parameters are being pulled from a much richer, much larger library of expert knowledge.
That's why it's so effective. In their comparison, a standard MoE might have, say, 128 total experts and activates 6 of them. The LatentMoE version runs with 512 total experts and activates 22 of them for the exact same inference cost.
And the performance jump validates that strategy.
It really does. On the MMLU Pro benchmark, the LatentMoE setup hit 52.87% accuracy, which just blew past the standard MoE baseline of 48.30%. That is a huge gap to gain just from smarter architecture.
Which proves that future gains aren't just about brute force scaling. It's about optimizing how and where those parameters are used.
100%.
Now let's talk about the training side, because Super and Ultra introduced 2 huge concepts there, starting with NVFP4 Training. Training in extremely low precision always seems to bring stability challenges, but the reward is just raw throughput.
The reward is incredible speed. Using the NVFP4 number format for pre-training lets them use native NVFP4 matrix multiplications, which can deliver 3x higher peak throughput than even FP8 on the new GB300 hardware.
So that's how they can efficiently pre-train these huge models on a 25 trillion token dataset.
Yeah.
But when you drop to that low of a precision, why does stability become such a huge concern?
Well, when you reduce the bits you use to represent a number, you lose dynamic range. You risk critical values just flushing to 0 or your gradients becoming unstable and spiking. So to counter that, they needed a really comprehensive stability recipe.
So what was the philosophy behind that recipe?
It was all about hypergranular precision management. They used things like fine-grained scaling, stochastic rounding on gradients, but crucially, they were very selective. They kept certain layers, the most sensitive ones, in higher precision to avoid catastrophic information loss.
And which components needed that special treatment?
They kept the last 15% of the network in higher precision. Also, the QKV and attention projections stayed in BF16, but here's where the hybrid architecture forced a very specific decision: the Mamba output projection layers.
What happened with those?
When quantized to NVFP4, they suffered massive flushes to 0. We're talking up to 40% in the Nano model. They had to mitigate that by keeping those specific Mamba layers in a slightly higher precision format, MXFT8.
That detail is so telling. It shows that even in an optimized hybrid architecture, different parts have vastly different tolerances, and that granular management allowed them to keep the loss difference between NVFP4 and BF16 extremely small.
Less than 0.6%, yeah. And most importantly, the downstream task accuracy tracked BF16 almost perfectly, so the efficiency gains came without a quality penalty.
Okay, now let's pair that with the second major training innovation, multi-token prediction, or MTP. This feels like a brilliant 2-for-1 benefit for both training and inference.
MTP is fantastic. During training, the model is forced to predict multiple future tokens, not just the very next one. This gives it a much richer look-ahead training signal. It encourages the model to plan ahead.
And that results in a measurable performance improvement.
About 2.4% on average across tasks like code and math. But then, during inference, those look-ahead predictions become high-quality draft tokens for speculative decoding.
Which is how we get those massive speed-ups in generation.
Correct. Speculative decoding lets the model check many tokens at once, bypassing that slow one-at-a-time loop. The NTP module they designed achieved a phenomenal 97% acceptance rate on the first 2 predicted tokens.
And that translates directly to faster, lower latency generation.
Which is crucial for any real-time agent.
We've covered architectural efficiency and training efficiency. Now let's tackle scale, the 1 million token context length. This is essential for things like analyzing a massive code base or running complex RAG pipelines.
And the architectural choices made earlier are what really enable this. Because the Mamba layers already integrate positional information inherently, Nemotron 3 avoids using rotary position embeddings ROPE in those few attention layers it keeps.
Which solves a very common problem. When you try to extend ROPE way beyond the length it was trained on, it just breaks.
It often does. By sidestepping ROPE, they avoid that out-of-distribution failure, which allows for much more robust context extension. And they actually showed that the MoE hybrid architecture itself adds resilience to this scaling.
We see that really clearly when they compare it to older architectures.
Absolutely. When they compared the Nemotron 3 MoE hybrid to the dense Nemotron 2 model, the Nemotron 3 MoE showed way better robustness when pushed to 1 million tokens. Its ruler score was 54.19%.
And the dense model?
It suffered an abrupt drop-off to just 23.43%. So the MoE hybrid degrades gracefully while the dense model just falls off a cliff.
And they also confirmed the model is actually using all that context, right? It's not just holding it in memory.
Yes, they did. They used a cumulative negative log likelihood analysis on repository-level code. They showed that the prediction error consistently decreases all the way up to the 1 million token mark. The model just keeps getting better the more context you feed it.
Okay. Finally, let's talk about the post-training process, which is critical for agentic capabilities. Multi-environment reinforcement learning.
Right, and this is about targeting the whole range of agentic tasks. Coding, math, tool use, long context reasoning. Instead of the old fragile staged approach, train on task A, then B, then C, they train Nemotron 3 simultaneously on a diverse set of RL environments.
And that simultaneous training gives you stability, which is so vital in RL, where you can see reward hacking or catastrophic forgetting.
Exactly. They got much more stable training. And this is where that high inference throughput comes full circle. It gives them a massive advantage during the large-scale rollout generation needed for stable RL.
What's the software stack for that?
They use an asynchronous architecture with GRPO, which is a policy optimization technique, and that whole stack, Nemo RL and Nemo Gym, is also being open source, which is a huge contribution.
It really is. And the last feature here seems so practical for deployment. Granular reasoning budget control.
This lets users actively manage that efficiency trade-off during inference itself.
How does that work?
You can specify the maximum number of tokens for the model's internal thinking trace. If it hits that cap, it just stops thinking and generates the final response based on what it has so far.
So if you're deploying an app where speed is paramount, you can fine-tune that accuracy-efficiency trade-off on the fly by just limiting the model's internal compute budget. That's the ultimate control knob for production AI.
It is. It gives the user fine-grained control over deployment cost versus the quality of the answer.
So to recap, what we're really seeing in Nemotron 3 is this comprehensive, full-stack approach to optimization. You have architectural efficiency with the Mamba-MoE hybrid, better model quality with LatentMoE, accelerated training with NVFP4 and MTP, and then unparalleled scale with the 1 million context length and stable RL.
And this isn't just a paper. The Nemotron 3 Nano is available now, with Super and Ultra coming soon.
Sure.
And the commitment to releasing the weights, the software, the recipes, the data, that's probably the biggest win here for the OpenAI community.
The whole strategy just seems to be leveraging two parallel efficiency vectors.
Right.
The architectural innovation with Mamba-MoE, and then resource optimization with things like NVFP4 and LatentMoE.
Yeah.
It tells us that the next wave of state-of-the-art models won't just be bigger. They're going to be fundamentally optimized from the ground up for deployment. It effectively turns what used to be restrictive inference constraints into entirely new architectural opportunities.
It's a fundamental shift in thinking.
Right. So the provocative thought here is, if efficiency techniques like these can unlock massive performance gains without increasing cost, how rapidly will the barrier to entry drop for developing and deploying really cutting-edge agentic AI?